All right, so let us continue. So, I will continue talking about arrangements today, and today I want to introduce a new concept called the notion of labels. So, again if you take a set of lines, so so the label of a point. So, if I take any point x, then I will define lambda of x, which is a label of x, is a number of lines of L lying below x. So, what it means is that if I take a vertical ray downward, count the number of lines that lie below that point. I do not count the point itself. So, line, if a point lies on a line, I do not count that line. So, think of it as a vertical ray that I drew is an open ray, the starting point does not count. So, in this case, for example, lambda of x is 3, am I right in this case? Okay. Now, k label, which I will denote as a k L, is the set of edges of A L whose label is k. So, if I look at this picture, so let us look at what the labels look like in an arrangement. So, this line, this edge, if you look at, this is label 0 because there is no line. If you all the points on this edge, the label is 0 because there is no line below it. Similarly, this edge also has label 0. Okay. Now, if I look at these edges, they are label 1, because if you take any point on any of these edges, if you draw a vertical ray, it will intersect exactly one line. So, for example, if you take it here, one line, you take a point here, one line. Now, if I look at these edges, this is label 2, okay, and so on. So, now I will draw label 3 and finally, this is label 4. So, what I did was, if you look at the edges of the arrangement, I layered them. I partitioned them into labels, and labels are polygonal chains. Each label, if you look at each label, it is a x monotone polygonal chain. It starts on the left infinity and it continues rightward and it finishes the right end. So, these are the labels, and if you have n lines, there will be exactly n minus 1 labels, because it is 0, 1 up to n minus 1 edges. Now, it is also clear by the definition that each of these labels is of course, it is a polygonal chain. So, if you notice the way I drew it, and it was not accident that I follow, if I look at a label, I follow an edge. So, I follow this edge, and when I reach a vertex, I switch. I was continuing on one line and I switched to another line. So, I then basically either I switched to this one and then this one and then this one, and so at every intersection point I reach, I always switch. So, that is how that happens. And it's hard not easy, it's not hard to see that the labels are X monotone chains. They will never go backward, they will always continue going forward, because if you have a label which goes something like this, then you have a contradiction, because what I am sort of saying is that these both of these points have the same label, and if you draw the ray starting from this point, it intersects at least one more line. So, they cannot be similar. So, the labels are always X monotone chains. Now, what we know is the total number of edges in the arrangement is n square, am I right? And there are n levels. So, the average length of a label, if I took a random label or to ask what is on average, the size number of edges in a label will be linear, because there are n labels and the total number of n square edges, and each edge belongs to exactly one label. So, the only average size of a label is linear. So, let me before say that, let me sort of say the following thing. Let me denote phi k l is the number of vertices on k level. Okay. Because this is a number of vertices on the label, and that is defined what the complexity of a label is. And what I said, on average, and as usual, define phi k n is the maximum of phi k l over all lines or n lines. This is the maximum complexity of a k label. So, what I said was that the average size of phi k l, average value, or on average, so what I said, that the average size of AKL is the k level is linear, but the question is what is the worst case complexity. Okay. And people believe that it is near linear, but it is not known, and it is a big open problem. So, let me sort of say what is known is the following, that phi k n is this is upper bound that is known, and what is known is that it is n log k. And this is also about 10 years old result, and one of the big open questions in discrete geometry is to give a tight bound on the complexity of a label. Now, one thing I should say is that if you look at the label 0, which is a green line in this picture, green polygonal chain, then one thing you notice is that A0L label 0 is nothing but the lower envelope. Okay. And if you look at the final label A n minus 1, that is the upper envelope. So, if you look at the final level, the level 4 on this picture, then that is upper envelope of these lines, and if you look at the level 0, that is the lower envelope. And remember that we talked about lower envelope and upper envelope in the context of Barnard diagrams. Now, I have drawn labels for an arrangement of lines, but one can talk about in the same way for an arrangement of one can define the notion of labels for an arrangement of planes in the same way. There is the definition is just remains the same, instead of lines, number of planes that lie below. So, you have a set of planes in 3D, the label of a point is a number of planes that lie below that point. Okay. And if you remember that what I had said was Barnard diagram corresponds to the lower envelope, nearest point Barnard diagram. And I had asked the question, what is the so if you look at the kth level. So, suppose if let us go back to the question of Barnard diagram, and if you remember what we had done was you started with a set of points, I mapped them to a set of planes, and if you look at those planes, that was the tangent to the paraboloid, and if you look at the k level in the arrangement of those planes. So, let us call them the following. H is the set of, let us call them as Voronoi planes. Voronoi planes was basically what, if you remember correctly, what we did was the following, and I will draw the picture only in 2D. So, just think about this picture in 3D, that you had basically instead of parabola, you will have paraboloid, and then you will have planes tangent to it. And the lower envelope correspond to Barnard diagram. And now, if you look at the k level, what will that correspond to? So, what does level k or AKH yes, it is a kth nearest neighbor. So, remember that what is Barnard diagram? Barnard diagram is the decomposition of the plane. So, that within each cell the nearest neighbor is the same, that is a Barnard diagram. Kth nearest neighbor, kth order, that is called kth order Barnard diagram. It is a decomposition of the plane in which the kth nearest neighbor remains the same. So, if you take the label k and project it on the plane, because in 3D when you take the k label, in 2D it was a polygonal chain, in 3D it will be a polygonal surface, and take that polygonal surface, project it on the plane, you will get the kth order Barnard diagram. Okay. So, that is one of the reasons why the labels were studied, because people were interested not only the nearest neighbor Barnard diagram, but higher order Barnard diagrams. So, we care about not only what happens to the nearest neighbor, but what happens to second nearest neighbor, and so on.
So, the k level Barnard diagram will be like bounded by curves, right?
No, it will still be it will still be bounded by lines, because what happens is it's still a plane. I am right that you have a set of planes, and when you intersection of planes is a line, when you project it, you will get a line. So,
but the cell of each point may not be convex.
No, cell will still be convex, but what will be the case is that a point may have multiple cells. So, each cell will be convex, but a point may have multiple cells. Okay. So, now what I want to do is, I do not know what the complexity or exact complexity of a label is, and I said this notion that on average it is linear size. So, I want to introduce the notion of what is called at most k label, and you will see in a minute why I care about this. So, if I want to look at most 2 level, not only look at the edges of level 2, but you also look at the edges of level 0, level 1 and level 2. So, that is at most k level. And let me again define phi k L is the number of vertices whose level is less than k. So, the phi k L is nothing but so you look at the vertices whose level is at most k. And the theorem is the following. Is order of n k, and actually it is theta. So, this sort of also verifies or supports the claim that the average size of a level is k, because I cannot bound the complexity of a single level, right. I cannot bound the complex single level, but if I take a band from any value up to k, let us say take the first k level, then the complexity of the first k levels is at most n k. Okay. And I am going to give you the proof of this theorem, because not only it is interesting in its own right, but the proof that I will give you is a very general and very beautiful technique in random sampling, and it is used in many different applications, not only in geometry, but beyond geometry, and especially when you are dealing with the problem with clustering in outliers and similar arguments are being used. So, and the proof is cute and short. So, I want to show you that how this one proves this theorem. But before I prove the theorem, any questions about the notions of at most k level or the notion of the level?
So these vertices are the intersection points.
The vertices are intersection points, because these are the vertices of arrangement, right. So, these are the vertices.
And the complexity, by complexity you mean
Number of vertices. When I say complexity of something, it means how many vertices are there.
So why are these vertices, counting these vertices, important?
You will see that why I care about that most k level, because it's a one thing I said, it's the same as kth order Barnard diagram. You ask, the question you ask is what's the complexity of the kth order Barnard diagram. We know that the complexity of the nearest neighbor Barnard diagram is only linear, but how big the kth order Barnard diagram will be, and that's not linear. It can be much larger, and it can be you'll see that's and you will see in some other why we care about at most k level. Okay. So, the proof is based on a random sampling argument, and I will do the following experiment. I will fix a parameter p, and which I will choose later, and I will for every line I will flip a coin, a biased coin, which has a probability of getting head, probability of getting head is p, and if I get a head, I choose it. So, basically what I am sort of saying is that I flip a coin for every line, and I choose a line with probability p. Okay. So, fix a parameter choose each line with probability p, okay, and let R be the set of chosen lines. Okay. So, what is the expected size of R? P times n, right? There is nothing deep there. Okay. Now, so what happened was that you had a set of lines and I chose a subset of these lines. So, let us say suppose this line was selected, this was selected, and let us say this was selected. Let me try again and hopefully we will do better. Suppose these 3 lines were chosen. Now, what I am going to do is I am going to bound the look at the label 0 of this set R. So, look at the so that is label 0 of R. So, it means that this is a label in this case. Okay. And let me do the introduce the following notation. It will be just easier. Let V K L be the set of vertices of A L whose level is K. Okay. All right. So, let me and as remember that our notation was then phi K L is nothing but the size of then what I want to do is I want to look at the phi 0 R, the number of vertices on the low envelope on the random subset of the lines that I have chosen. Now, and I want to look at its expected size, because it is a random subset. So, the R is a random subset and phi 0 is a low envelope which is a random quantity, and I am looking at its expected value. So, its expected value is nothing but you look at all the vertices in the arrangement, and this is basically ask a question, what is the probability V R belongs to V 0, right, because that is by definition of expectation that a vertex on the random subset on the low envelope, these vertices, these are nothing but the vertices of the original arrangement. For each vertex you ask the question, what is the probability, and because the vertex is chosen or not chosen will be there. So, it is a 1. So, normally you say that p x is the value of x, but the value of the its indicative variable. So, it is just a question of probability. Now, this what I can do is I am going to write it in the following fashion. So, I took the set of vertices, divided them into the labels, because if you look at all the vertices in the original arrangement, they have certain label, as we had talked about earlier, and this is the notation I used. So far there is nothing deep has happened. Now, let us ask the following question. Here you have a vertex of the original arrangement which lies on which is an intersection of point of 2 lines, and let us say its label is j. Okay. So, So, let us ask the following question. So, let me write the following question. Suppose you have a vertex V and V belongs to VJL. It means its label is J. So, when does V appear on? So, when does V appear, this vertex appears on the lower envelope of the random subset of lines? Yes. So, what is the problem? When does some arbitrary vertex will appear here? So, the two things have to happen, am I right? So, let us say, so since its label is J, then if you draw the lines below here, there are J other lines that lie below it. Two things have to happen for V to appear on envelope. These two lines should have been chosen and none of these lines should have been chosen, because if any of these lines is chosen, this vertex V will not appear on the lower envelope. Okay, so, let us write this. So, let us look at this, call this line L1, L2. So, one condition is that L1, L2 they are chosen in R, and let us call this line as the killing set in the vertex, because if any of these lines is chosen, then the vertex does not appear. So, these are the lines that kind of kill them appearing on this one. And second set is KV is empty, right, because none of these lines should have been chosen. So, if you take an arbitrary vertex of the arrangement, blue vertex, which is an intersection point of two lines, if its label is J, then there are J lines that lie below this vertex. In order for this vertex to appear on the lower envelope of the random subset of lines R, these two lines should have been chosen and none of these lines should have been chosen. So, what is the probability of this happening? Not p to power j. Yes. So, then basically we just write it this. Oops. This comes from the probability of this happening is p square. This condition is that none of the lines is chosen. The probability of a line not being chosen is 1 minus p, and these are j lines. So, it is j. Okay. Now, that is the main thing, and now I will do some manipulation. So, this is, one can write it as j is k. Now, this probability, it depends not on the individual vertex, it depends also. So, this is p square 1 minus p to power j, number of such, this basically multiplies the number of vertices in the label, which is by definition is precisely phi j l, the size of V j l. This one can write because I just k is at j is at most k. So, I can write this way phi j l, and I can take this first two terms outside. So, it becomes p square 1 minus p, and this quantity j is equal to 0 to k phi j l is nothing but phi k l by definition. So, this was the definition of phi k l at most. So, what it means is, now if you put it other way, phi k l is at most expected value of phi 0 r over p square 1 minus p to power k. Okay. Now, what we do is we set p to be 1 over k. Okay. Then what you get is p square becomes k square 1 over p square, so k, so you get k square k. Now, what is the expected value of the low envelope? Now, if you have a set of n lines, when your set of whatever lines you have, lower envelope is, if remember, it's nothing but the convex hull, and you know the convex hull has linear complexity. So, this is also a convex polygon which is intersection of n lines, and you know that has size is linear. So, its size is linear, all right. Now, what we know is that the expected size of R is P n, we said, which is n over k, and size is linear. So, you get n over k. Okay, right. So, what you get is the what is, can you give a bound on this one? It is roughly 1 over e. So, it becomes e, am I right. So, this is becomes e times n k. So, which is order of n k. So, notice what I did here. Now, I never used the fact that these were lines. The only thing I used to bound this quantity was that these two quantities, these two things were true. That this, I tried to count this number of vertices, and this number of vertices were intersection points of two lines, two objects, and the probability was that these two objects should not have been chosen. So, these two objects should have been chosen, these which are killing set, that were not chosen. And one can define this an abstract framework, that you have a set of objects. One can define for every object set of which is being derived from these objects, geometric objects, that what is called a defining set, because this two lines define this vertex. One can talk about defining set, and one can talk about the killing set. And then you can ask a question, what are this the probability of the vertex is being chosen, and then so this is very general framework. And other thing is a random sampling argument is done. So, now one can extend this argument also in 3D. And one thing you notice is, until the reason I wrote it, this is an important part to read.
How is the end result deterministic? I mean, you use some random sampling, and how is the end result deterministic?
Because there is no randomization in this part, right? Because what I proved to you is the following. This is what I proved to you. This quantity, right? There is no randomization on the part of L. The only thing was it's a part, and this is what I am sort of saying, that this is, that's why I say it's a beautiful technique, that a randomization technique is being used to get a worst case bound on some geometric quantity, combinatorial quantity, and that's a sort of is very powerful probabilistic argument. Now, how many of you have seen probabilistic arguments to prove? So, typically probabilistic arguments are used for existential proof, or to prove some sort of probabilistic methods to show whether something is true or something is not true. Here the probabilistic argument is being used to count certain thing, and it is used in many different, sort of this technique is used in many different domains. So, what I want to say is that this is the important part, equality. So, if you choose P to be k, and I do not put this quantity of phi 0 r, then what one can write is the following. So, if I look in the worst case bound, so this is phi k n, P I will choose 1 over k. So, it is get k square, and this is E, I will just ignore this part, k square times E, and expected I will replace it the worst case bound, because size of R is n over k. So, what you get is basically so, if I think of an abstract framework, if I have this notion of this levels 0 or level 2 up to 1 k, then basically what you say is that if some objects are being hidden by k objects, then this is the bound you get. And I will give an application that why it is in more general setting. But any questions about the proof? It takes a while to digest this proof, because it is a, as he said, it is a kind of a counterintuitive, because I am using randomization to bound something that is not randomized, it is the deterministic worst case bound. Let me give you one sort of example of this generality of this framework, and then I will give you two applications that why we care about labels. So, suppose you have a set of disks. Okay. So, let us call D and disks. And I will define a label of a point now. I will define the label of point x is the number of disks that contain x in their interior. Okay. So, for example, if I look at this point x, its label is 1, 2, 3. If I look at this point, although it lies on the boundary of two disks, but it does not lie in the interior of any disk. So, that is its a label is 0. So, what is label 0 in this case? Say it again, say. Yes. So, you look at the boundary of the union, boundary of the union is label 0. So, again if I define the arrangement, and I can talk about A 0 D is the boundary of the union, right. Now, we can talk about similarly A K D, and we can is the K label, and again I can talk about the phi K D, and also I can talk about the phi at most K D, okay, at most K label. Now, first lemma which I will tell you, for now you should believe me that if you have a set of disks, how many vertices can appear on the union, on the boundary of the union? There are n square vertices, am I right? There because in total in the arrangement there are n square vertices. How many of them can appear on the union? Does anyone have a guess? Pardon? 10? N? 2n. Anyone else? So, how many of you believe it is an order of n? Or how many of you do not believe that it is not? How many of you believe it is more than it is a superlinear? Come on, you have to have an opinion. This is democracy. Pardon? Should be linear? Yes, it is linear, and either I will give you a homework problem if I do not have time. If I have time, then I will give you the proof. So, phi 0 D is order of n. Okay. Then now, I can use this result to prove that the number of vertices that lie in the interior of at most k disks is only n k, and the proof is identical to what I gave here. Because again, if you look at instead of lines, if you look at disks, am I right? Then if you and I choose a random set of disks, let us suppose I chose this random disk set, and I ask you a question, what is a complex, what, so if I choose a vertex of the arrangement of this blue vertex, ask the question, what is the probability that it appears on the boundary of the union of the red disks? And if its label is j, it means it lies in the interior of j disks. Then again the same thing condition should happen, is that, well, you remove from the lines, you remove it to say that the two disks whose boundary defines this vertex, they should be chosen, and none of the disks that contain this vertex in its interior, in their interior, they should be chosen, and the same thing goes on. So basically verbatim the same proof basically just goes through, and I will get to this, this is what I have written in the bracket square, this line, because what will happen is that the number of vertices whose label is at most k will be the number of vertices on the union of the random subset times k square. And now I know by lemma 1, I know that the boundary of the union has only linear number of vertices. So again what I can write here, the way I wrote it here, that phi 0 r is n over k, and the same thing will go through, and that will do it.
So is there any other way of proving this?
Yeah, there are other ways of also proving, but this is the cleaner way, nice way of doing it. Okay. Now that I have given you these two stuff, now let me give you examples why we care about it. So let us look at the following problem, which is suppose there is a big disk which is some kind of a region, and you have a set of points inside this region. Let me start asking you a simpler question. So this, suppose this is radius is some big R. Find a, let us call this one as big D, placement of a disk of radius 1 inside D such that gamma does not contain, and let us say S is a P 1 . So the question I want to ask is there a, let us say, a disk of radius 1, can I place a disk of radius 1 inside this inside the bigger disk, so that it does not contain any of the input points. So think of the point as a sort of obstacles. So the disk cannot contain any of these input points.
So increase the points to the half radius.
Okay, go ahead. And then
you see whether the point
Also
lies
reduce
within
the bigger disk.
that's right. So what you do is that, like, so to reduce this one to r minus 1, and draw a disk of radius 1 around each point. Am I right? And if there is any okay, and then what you do is you look at inside this bigger red disk and outside it, and compute the union of this disk radius 1 disk and see if there is a point there. If I find a point, then it means that if you put a disk of radius 1 there, it will lie inside the disk and it will not contain an input point. Now we know that the union of the disk has a linear size, right, and I have not told you how I compute it, but when I give you the proof how you, why it is a linear size, you will see the proof also how you compute it, and then it will basically do it. Now if I change the problem something like this, maybe it is too stringent to require that you does not contain any point. Let us say I allow you to contain at most k points. Okay.
look for the
That is right. So, it means that you want to compute at most sort of k, at most scale level k. Now, let me sort of flip the problem. So, this was a placement what is called the largest empty placement, or you can ask the following question. Instead of I give the disk of radius 1, you can ask find me the largest disk that I can place inside this D that does not contain any point, in which case you need to do some kind of a binary search on the radius and see how you find the larger disk. Or you can ask the question what is the largest disk I can put inside it, so it does not contain any of the input point. So, think of these points as a constraint that you cannot contain, and you ask the question. And when you allow some outliers, because when I say at most k points, those k points are kind of outliers. So, whenever you have to deal with the outliers, then this at most k level shows up. So, here is another problem, which is a kind of a dual of this problem. Now, I give you a set of points. Is there a disk of radius 1 that contains all the points? Then what will you do? It is very similar to what I asked earlier, but now I ask a question, is there a disk that contains all the points?
We draw circles of radius 1 around all these and find if there is a point of level n.
Intersection. So, that is intersection, am I right? They do it. Now, what I ask the question, again I play the outlier game some of times, because there might be some outliers, because okay, most of the points are clustered here, but there might be some points because of measurement error or something that may happen, which is like whenever you are doing clustering, you always want number of times you want to do the outlier. So, say I ask the question, is there a disk that contains all but at most k point, all but k points? Then again I can define the label, but I have to define the label differently now, or you can talk about label n minus k, you can talk about it doing it. So, that is why this at most k labels come. Here is a final problem, that example I want to give you, which is a classical problem in classification and machine learning, is the following. Suppose you have some data, these are some positive examples and these are some negative examples, right. So, for example, what happens is that this is many example, it comes everywhere in the classification problem, but for example, like want to look at understand the disease. So, what you do is you have some symptoms, you think that these are the symptoms that cause disease, you want to check. So, you have certain defined some symptoms, and then you look at the patients who have that disease versus the patients who do not have that disease. So, patients are the positive examples, and the patients who do not have, people who do not have the disease, those are negative examples. And the question you want to ask is there a simple rule that can separate them? And the simplest rule, that is what is used in machine learning and classification, is called linear classifier. So, what that means is there a line, if suppose if this were in two dimensions, is there a line that separates blue points from the red points? Okay. So, the question I want to ask is there a line? So, R is a set of red points, B is a set of blue points. Is there a line that separates red and blue points? Okay. Now, suppose let us say there are two possibilities. If I line, let us say blue points lie above the red line, above the line, and red points lie below the line. Okay. So, let us say suppose our life was very simple, and here were all the okay. Then what you sort of you want to check that, then what you basically want to do is you compute the convex hull, and you compute the convex hull of red points, and you check whether these polygons are disjoint. Okay. So, if they are disjoint, then there is a line that separates them. Okay. So, that will do it for you. But now again there might be outliers. So, it might be too stringent, but what happens, you cannot find a plane that really separates them. You say I allow k. So, where the side that contains most of the blue points, you allow at most red k points, and the side that contains red points, you allow at most k blue points. Then how do I do it? think of duality. If I dualize these red points and blue points, right, I am going to get a set of red lines and I am going to get a set of blue lines. All right. If they were separable in this example, where they were separable, it means there is a point that lies below all the blue lines and above all the red lines. It means lies below the level 0 of these blue lines and it lies above level n minus 1 of the red lines. Now, but I allow some up to k outliers, then instead of level 0 you want to look at level k, am I right? You take the k level of the red lines n minus k level of the blue lines and ask the question, there is a point, these are the two polygonal chains, and the question you want to ask is there a point that lies below this polygonal chain above this polygonal chain, and that you can do. So, that is why they sort of again you need the question, and the running time of this will be basically depending proportional complexity how fast you can compute those labels. So, that is why we care about this is some of the reason why we care about the labels that happens. Okay. Any questions? Now, let me conclude by just give you proving this theorem that the union of disks has linear complexity. I will give you two proofs. One that you have seen it, from which follows from what I have talked earlier. So, here is a set of disks. Let us say d I is send a I and r I is its radius. So, radius is r I. So, the equation of the disk is x minus a I square, oops, so if the point lies outside this disk, it means that the quantity this should be true for the point. For a point x y that lies outside the disk, this inequality should be true, and if it lies in the outside the union, it should be true for all i's. If a point lies outside the union, if x so, if you write this one as x square plus y square and this one you map it to z, that our usual lifting transform, then what you get is so this is equation of a plane, and what it says is that if I took the circle and I took the disk and mapped it to a plane into a disk mapped to a half space in 3D. This is a standard lifting transform that you have seen earlier, and if a point lies in the exterior in the outside the union of the disk, it lies above all these half spaces, and as you sort of see in the intersection of n half spaces has linear complexity, has only linear number of vertices. So, what we know is that, so let us call this as h I, then because it is a convex polytope in 3D and it has a linear size, that is basically does it, and that implies that union of disk has linear complexity. Now, there is another proof which is nice, and a different proof is the following. Suppose you have a bunch of disks, you construct a graph as follows. The vertices of the graph are the center points of the disks, and you connect the two disks by an edge. You connect two centers by an edge if the intersection point of those two disks, at least one of them, appears on the boundary of the union. So, for example, here you connect. Well, let me do the following, put this one also. So, this is a graph you get, and the claim is that this graph is planar. Okay. I will not prove it. It's not very hard. It's just high school trigonometry, but using high school trigonometry, you can argue that this graph is planar. And if the graph is planar, it has only linear number of edges, and that implies that union complexity has linear number of edges. So, that the reason that the second proof is nice is it does not use the fact that these are real circles. So, let me just conclude by saying the following. Suppose you have some shape which is very strange, but it has the following property, that if you take any pair of them, they intersect in at most 2 points. Okay. These are called pseudo disks. And the complexity of the union of pseudo disks is also linear. The proof that I sort of the graph is planar, you can do something similar here also. Centers are not very well defined, but one has to be little careful, and you can still say the graph is planar. And why the pseudo disks are important? Now, if you remember when I gave the motivation for the arrangements, and one of the things I said was motion planning, that you had the, let us say, set of obstacles, and then you had a square B, and when I generated this expanded obstacles, if you remember, all right, something like the extended obstacles you get. What you can prove is that now extended obstacles, they intersect, because all the original polygons are disjoint, but after you expand them, they intersect. But what you can argue is that any pair of them will intersect on at most 2 points. So, these are pseudo disks. So, it means that you may look sort of pretty nasty stuff after expanded, but the total number of vertices are still linear, and you can compute them, and that sort of implies that you can still do motion planning easily. Okay. So, let me stop here.